Hi, welcome back to educator.com. Today we're going to talk about graphing and asymptotes in a nutshell. In the past two lessons, we've learned how rational functions work. We've studied and come to understand their behavior along both vertical asymptotes and horizontal/slant asymptotes. In this lesson, we'll use this knowledge to learn how to graph rational functions. It's strongly recommended that you watch the previous lessons beforehand because we'll be pulling from that work. Also, while we won't be going over it in this lesson, using a graphing utility, whether it's a calculator or a program or something even on a smartphone, it can be an absolutely great way to understand how rational functions work. Playing with function graphs can quickly build your intuition. Just like it can build your intuition for any function, being able to play around and change how things are working and what your denominator is and what your numerator is will build a really great intuitive understanding of how this stuff works much faster than trying to do it all by hand. You'll be able to get a really good grasp of how this stuff works, be able to see it in your mind's eye in a way that you just can't develop by trying to do 10 problems in hand, because you can just do like 100 of them in a matter of a few minutes if you're just playing around on a calculator. So I highly recommend take the chance, use a graphing utility and play with something. If you haven't already checked it out, there's an appendix to this course all about graphing utilities, graphing calculators, all that stuff that can give you some idea of how to start and that sort of thing, because they can be really useful for helping you in a course like this and in future math courses. All right, let's get started. The majority of this lesson is going to be about a process for graphing rational functions. By following the steps of this process, you'll obtain what you need to graph. You'll get all the information that you need to make a good graph. This process also gives you a way to analyze rational functions in general, though. So it's not something that you can only use when you want to graph a function. Just if you want to look at a rational function and get a good idea of how it works, you might find this process useful. So you might use it even if you don't need to graph anything. Let's go. First step, a rational function starts in the form n of x, d of x, where n of x and d of x are both polynomials, so this division. It's useful as your very first step to begin by factoring n and d. While this won't directly tell us anything, factoring the numerator and the denominator don't immediately tell us anything directly, it's very useful in the coming steps to have the numerator and denominator broken into smallest factors. A lot of our steps are going to revolve around having these things already factored, so it's something to get out of the way right from the beginning. So we're going to have a running example as we go through this. If we have f of x equals x squared minus 3x plus 2 divided by 2x squared minus 2x minus 4, we could factor this and we'd get x minus 1 times x minus 2 for the numerator divided by 2 times x plus 1 times x minus 2 for the denominator. So we started off by factoring it by just breaking these into their factors. By seeing what these things become, we're able to get a good sense for later steps. It'll help us out in the later steps. So we just reformat it with the numerator factored and the denominator factored, and that's all we do for right now. Second step, find the domain. Find the domain of the function. Remember, we can't have division by 0. That's one of the critical ideas here. So we want to find all the x values where the denominator is 0, because those are going to be forbidden. We do this by finding the zeros, the roots of d of x. So find the zeros of our denominator function. And since we just factored the denominator function, this is going to be pretty easy, right? We just factored it in our example into x plus 1 and x minus 2, so we see at this point that we wouldn't be allowed -1 or +2 because they would cause a 0 to pop up. So each of the zeros of our denominator is not going to be allowed in the domain. So they will not be allowed in the domain if they are a 0 of our denominator polynomial. All other real numbers are in the domain because everything else is fine for a polynomial. The only problem is when we're accidentally dividing by 0, so we just have to clip those out. Those are the forbidden locations that we can't take in. Now, each of these forbidden locations will become one of two things. They'll become a vertical asymptote if the 0 does not occur in the numerator, or they'll become a hole in the graph if the 0 does occur in the numerator. Next step, simplify the function. Once we've found the function's domain, we can simplify the function by canceling out any factors that are in both n of x and d of x. So we noticed that we had x minus 2 on the top and x minus 2 on the bottom. We have common factors, common linear factors, so we knock them both out and we're left with x minus 1 over 2 times x plus 1. It's important to note that we couldn't do this in our very first step, in our first step factoring, because if we did that, we wouldn't be able to find all the forbidden x values, right? There is a forbidden x value at x equals 2, right? So that's something that we're not allowed to have from this. So the only way to find that is if we haven't already gotten rid of it. If we start off by canceling it, we'll never realize that x not equal to 2, right? Because x equals 2, that horizontal location of x equals 2 is forbidden. So if we cancel out that factor before we notice that it's a forbidden location, we'll never be able to figure that out. So we have to get that information before we cancel it. And that's why we do factoring and then check the domain, then simplify. Next step, find vertical asymptotes. Once the function is simplified, we can find the vertical asymptotes. The vertical asymptotes will occur at all the x values that cause the denominator, after we have simplified the denominator, to become 0. So all the zeros of our now newly simplified denominator. So if we have 2 times x plus 1 in our denominator, we're going to get a vertical asymptote at x equals -1, because that will cause our denominator to turn into a 0. Next step, find the horizontal or slant asymptotes, or figure out if it has absolutely none of those. Let n be the degree of the numerator, so n is the degree of our numerator, and m is the degree of our denominator. Then there are a total of 4 possible cases. N is less than m. The denominator is the degree of the numerator is less than the degree of the denominator. Our denominator grows faster than our numerator, means that it will eventually be crushed down to nothing. The whole fraction will be crushed down to nothing, and we have a horizontal asymptote y equals 0. Another possibility, if n equals m, the degree of the numerator is equal to the degree of the denominator, then there will be a horizontal asymptote at a height given by a ratio of the leading coefficients, because they're both growing at the same sort of class of speed, so we need to compare how their fronts go, right? If we've got effectively 5x to the 5th divided by 2x to the 5th, the other stuff has some effect, but in the long run won't be as important, then it'll turn into 5/2 because the x to the 5ths cancel out. So that's one way of looking at it. So n equals m means that we get a horizontal asymptote based on the ratio of leading coefficients. Next, n equals m plus 1. That is a slant asymptote. We will have a slant asymptote, and we find that by using polynomial division. You can also use polynomial division to find the horizontal asymptotes, but it's pretty easy and fast to find it just by comparing the leading coefficient, so we don't worry about that as much. And then finally, if we've got n greater than m plus 1, there is no horizontal or slant asymptote whatsoever, because the numerator is growing so much faster than the denominator that it's not going to be a horizontal thing that it goes to. It's not even going to be a slant that it goes to. It's just going to blow into something even larger and more interesting. But we're not going to worry about that in this course. F of x equals x minus 1 over 2 times x plus 1. We realize, hey, this is a degree of 1, this is a degree of 1. So now we go and we compare our leading coefficients. So we've got a 1 on the top, a 2 on the bottom. So we get a horizontal asymptote of y equals 1/2 in our running example. Sixth step, find the intercepts. By finding the x and y intercepts, we've got a couple points in the graph that we just have to start with. Now, it is possible for a rational function to be missing one type or both. So it's possible that these things won't be there because the location of our y-intercept, x equals 0, that could be a forbidden location, right? And all the places where we cross over, it could either not cross the x-axis at all, or the locations where it would cross the x-axis are actually disappeared holes in our graph, so they aren't technically intercepts. So it is possible to be missing these things. But if we have them there, they're nice and they're not that hard to find. The x-intercepts occur wherever the function has an output value of 0, right? Because that means we have a height of 0, so we are on the x-axis. We are an x-intercept with a y height of 0. Thus, all of our zeros mean that our numerator is at 0. This is all the zeros of our simplified numerator. So x minus 1, what are all the places where that gives a 0? That gives us a 0 at x equals 1. So at x equals 1, we get a 0 out of it. So if we plug in 1, we get a 0 out of that because the numerator is now at 0. The y-intercept is where the function's input is 0 because that'll put us on the y-axis. So we plug in the x value. Sorry, I might have said the wrong thing there. I'm not quite sure what I said. The y-intercept occurs where the function's input, its x value, the x that we're plugging in, is 0 because that'll put us right on the y-axis. So just evaluate our function with a 0 plugged into it. So f of 0 to find it, we plug in 0. So 0 minus 1 over 2 times 0 plus 1 from our simplified function. So that simplifies to -1 over 2. So we get 0, -1/2. So we've got some points to start off with when we're plotting. Final thing, draw the graph. Now that we have all this information on our function, we're ready to graph it. Begin by drawing in the asymptotes on the graph and plot the intercept points. If we need more points to graph the function, and we're probably going to need more points since the intercepts, really, there are only a couple things that come out of the intercepts, evaluate the function at a few more points as you need and plot those points as well. So plot those extra points, and then at that point you can start drawing in curves. It's useful to plot at least one point between and beyond each vertical asymptote. So if we've got vertical asymptotes like here and here, you'd probably want to make sure you plot at least one thing in each of these locations, and there's a good chance you'll need a couple more than that to be able to really get a sense for how the thing is going to come together as a picture. So something to think about. Then draw in the graph, connecting the points with smooth curves and pulling the graph along the asymptotes. And of course, if you're not quite sure where it goes, how it works together, you can just plot in even more points and you'll get a better sense of how the picture comes together. Make sure you know which direction, positive or negative, the graph will go on either side of your vertical asymptotes. And one last thing, don't forget that the forbidden values, our forbidden x locations, will create holes in the graph, right? We're going to be having these locations that aren't really there, which we'll denote with an open circle to say, well, we would be going here, but it actually is missing that location because it's a forbidden thing because it will cause us to divide by 0. So we're either going to have vertical asymptotes, which we'd never get to anyway, or we're going to have actual holes in our graph, which we denote with a hole of a just round circle that has nothing inside of it. So don't forget that you have to remember about the holes when you're actually drawing in the graph. Not every graph will have holes, but if yours does have forbidden x values that aren't just vertical asymptotes, you'll need to do that as we're about to see. F of x equals x squared minus 3x plus 2 over 2x squared minus 2x minus 4. We simplified that into x minus 1 over 2 times x plus 1. We figured out that our domain had forbidden values at -1 and 2 because they caused our original denominator, not just our simplified denominator, to turn into a 0. We're not allowed to divide by 0. To figure out our vertical asymptote, we looked when does our denominator go to 0, when does our simplified denominator go to 0? That happens at x equals -1. To find our horizontal asymptote, we noticed that we have degree of 1 on the top and the bottom, so 1 over 2 gave us y equals 1/2 as a horizontal asymptote. So we plot our horizontal asymptote, we plot our vertical asymptote, and we also figured out our intercepts. 0 comes out as -1/2, so we plot that point right there, and 1 comes out as 0, so we plot that point right there. Those are our intercepts. Now, that's not quite enough information, for me at least, to figure out how this is going to graph, so we decide let's plot a few more points. We try out -2, -3, because -2 is one step to the left of our asymptote, so we plot in this point. We plot in -3, that comes out there, so we got -2 at 3/2, -3 at +1, and then also we can say, well, we're not allowed to put in 2. But we're still curious to know where that would be if it was there. So let's see where 2 would go if it wasn't a forbidden location. Remember, it's forbidden here because it caused us to divide by 0. But in this one, it doesn't actually cause anything weird to happen. In our simplified version, because we've canceled out the 0 over 0 effectively, since we've canceled it out, it doesn't cause anything weird to happen. So we can see where it would go by looking at our simplified version. So if we plug 2 into our simplified version, we get 2 minus 1, 1, over 2 times 2 plus 1, 2 times 3, 6. So we get 1/6. So we plug in not just a point, but a hole to tell us, hey, look, there is where you would go. You'll run through that location, but you're not actually going to occupy that. So at this point, it seems like we're starting to get enough information. One last thing we might want to figure out is which way are we going to be going on each of these asymptotes. We probably can get a sense at this point. So if we plugged in, say, -1.0001, if we were just to the left side of our vertical asymptote, then over here we'd have 2 and -1.0001 plus 1. And up here we'd have -1.0001. So on the top, we'd have negative minus a negative, so it's a negative. And then divided by 2 times negative plus 1, -1.0001, so just a little bit more negative. So it's going to be a negative number down there. 2 doesn't change it from being negative. So we've got a negative over negative, which cancels out to a positive. So it's going to come out being positive on this side. So we're going to be going up with our vertical asymptote on this side. If we do the opposite, -0.999, like this, then if we plugged in -0.999 minus 1, we see that's going to wind up being a negative. And then divided by 2 times -0.999 plus 1, we see -0.999 plus 1. That stays positive just barely. It's a very small positive, but it is positive. So we've got a positive on the bottom. Negative divided by positive, that remains being negative. So on the right side of our vertical asymptote over here, we are going to be going down because we're going to be having negative values coming out of it. So now we know which way it should be going, and we know on our horizontal asymptote, it's just going to stay on the same side and run with it. We draw all these things in, and sure enough, that's what happens when we draw in our picture. Great. Test intervals. This is a useful idea that can occasionally be used. We didn't use it in our initial 7 steps, but it is something that we kind of vaguely used it without explaining it on the last thing where I said we knew that we were going to have to stay under the horizontal, below the horizontal in these various locations. Let's see what it is. A useful concept for graphing this is the idea of the test interval. Because a rational function is continuous. Remember, there's no jumps in a rational function because it's built out of polynomials. So there can't be any jumps between vertical asymptotes. We know by the intermediate value theorem, since we aren't allowed jumps, that a function can only change signs at x-intercepts, where it crosses from positive to negative, so it can only change signs when it hits a 0 to be able to go from positive to negative, or vertical asymptotes, because after a vertical asymptote, it does jump. This means we can put our x-intercepts and our vertical asymptote locations in order, and then break the x-axis in intervals. In each of these intervals, we can test just one point, because we know we can't jump until we hit an x-intercept or we hit a vertical asymptote. We can't flip signs. So we can test just one point to figure out, is it going to be positive in that interval or is it going to be negative in that interval? So in each of these intervals, we only have to test one point to figure out positive or negativeness in there. So if we have f of x equals x minus 1 over 2x plus 1, our example that we've been working with this whole time, then we've got a vertical asymptote at x equals negative 1, and we've got an x-intercept at x equals positive 1. So that means we can go from negative infinity, right here, up until negative 1, our first interval location stopping. And then from negative 1 up until 1, our next thing, from negative 1 here to positive 1 here, and then 1 out into infinity because we don't have any others. So there's 3 intervals, and the function is going to maintain its sign within that interval. So let's test any point. So notice negative 2 is inside of that interval, so let's try out negative 2. We plug in negative 2, and we get negative 3 divided by negative 2, which becomes positive 3/2, so it is positive everywhere between negative infinity and negative 1, it's positive. Negative 1 to 1, let's look at 0. 0 is definitely in that interval. We plug that in, we get negative 1 divided by 2, so we get negative 1/2. That means it's going to be negative everywhere inside of that interval. And 1 to infinity, let's try out 3. 3 is in there. We plug in 3, we get 2 over 2 times 4, so we get 1/4. Because we had 2 over 8. So 1/4, but it is a positive more importantly, so we know we're going to be positive everywhere from 1 out until positive infinity. If you go back just a little bit to the previous graph where we saw the thing actually get graphed in, and pause it there, you'll actually be able to see that it winds up being always positive between negative infinity and negative 1, always negative from negative 1 to positive 1, and always positive from 1 out to infinity. You'll be able to see that in the graph, so that's the idea of test intervals. All right, let's look at some examples. F of x equals 3 divided by x plus 2. So our first step, let's figure out what is forbidden in our domain. So our domain can't cause anything to go to 0, so x plus 2, when is x plus 2 equal to 0? That happens at x equals negative 2, so our domain will not allow negative 2 because we do not want a denominator to allow a 0. Next, what are our vertical asymptotes? So vertical asymptotes, that's going to happen when, are we simplified? Yeah, 3 divided by x plus 2, it's already simplified, so that's going to be whenever the denominator is 0. So we've got a vertical asymptote at x equals, not 0, but x equals negative 2, where the denominator becomes 0. So our domain location that is not allowed is our vertical asymptote here. And finally, a horizontal asymptote. What will this go to in the long run? Horizontal asymptote. So in the long run, we've got a numerator's degree is 0, and our denominator's degree is 1. So in the long run, the denominator will grow and eventually crush our numerator to effectively nothing. So in the long run, our fraction goes to 0, so it has y equals 0 as its horizontal asymptote. Now, it would probably be a good idea to find some intercept locations so we can have a better idea of what's going on here. So let's see at 0, where are we? So at 0, we plug in 0. 3 divided by 0 plus 2 gets us 3 over 2. Do we have a y-intercept? Yeah, we have a y-intercept. That's what we just figured out. Do we have any x-intercepts? No, because the numerator is always 3. The numerator never goes to 0, so there's not going to be any x-intercepts. Let's draw in our graph, and then we will fill it out. So, whoops, that got kind of curvy. I'll erase that real quick. So we know that -2, because that's our vertical asymptote, is sort of the most interesting location. So we'll give a little extra space on our left side. So 1, 2, 3, 4, 5, 6, 1, 2, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Okay, so we know at the -2, and hope you don't mind, I'm just not going to mark it down. I think we can see pretty easily just counting out what those are. We just know those tick marks mean 1. So we've got a vertical asymptote at -2, and we have a horizontal asymptote at y equals 0, which is just our x-axis. Great. All right, so how can we draw this in? So we have 0, 3/2, so it's 0, 3/2, we're right here. Now, we probably want some more points. That's not quite enough information, so let's try some points. Let's go just one to the left of our vertical asymptote. So let's try out -3. We plug in -3, we get 3 divided by -3 plus 2, so -1. 3 over -1 gets us -3. Let's try -4 as well. We plug in -4, 3 over -4 plus 2, -2, so 3 over -2, or -3/2. We plug in -5, and we'll get 3 over -5 plus 2, so -3, so we'll get -1. So we can plot this stuff on the left side now. At -3, we are at a height of 1, 2, 3, -3. At -4, we're at 3/2, and at -5, we're at -1. Well, let's go on the other side. Let's look at, we've already got this point here, so let's try -1. At -1, 3 divided by -1 plus 2 becomes +1, so we are at +3, because 3 divided by 1 is 3. At 0, we already figured out we're at 3/2, and at +1, we're going to be at 3 over 1 plus 2, so 3, so we'll be at 1 there. So +1, we are at 1. At -1, we are at 3. Great, so at this point we've got a pretty good idea. We can see that we're going up here, we can see that we're going down here. We could plug in, -2.00001, and we'd see that'd be 3 divided by a negative, so we're going negative, and -1.99999 would be 3 divided by a positive, so we're going to go positive. But we can also just see from enough points that we have at this point to see where the curve is going. So we draw this in, it curves. As it approaches the asymptote, it curves more and more and more and more and more. The other way, it's going to curve and approach its horizontal asymptote, and it approaches it, but it never quite touches it and goes out that way. Similar thing going over here. It curves, it approaches the vertical asymptote, won't quite touch it, and here it curves, approaches the horizontal asymptote in the long run, but it doesn't quite touch it either. Great, and there we are, first one. Next one. Graph f of x equals x plus 1 over x cubed plus x squared plus x plus 1. So first thing we want to do is we want to factor this. Top is still just going to be x plus 1. What's the bottom become? Well, we know that there's going to be an x plus 1 factor in there. We can figure that out by plugging in -1. We see that it would work. But we can also eventually we'll eventually factor it into x plus 1 times x squared plus 1. So our domain, what is not allowed by our domain? Our domain does not allow x plus 1, so x is not allowed to be -1, because -1 plus 1 would give us a 0. So domain is not allowed -1. Does x squared plus 1 provide anything? No, x squared plus 1, that's an irreducible quadratic. There's no roots there because x squared plus 1 equals 0. It's always going to remain positive. You can't solve x squared plus 1 if you're using real numbers, so we don't have to worry about a hole appearing there. So our only issue is that equals -1, so we disallow -1. -1 is a forbidden location. Now at this point we can simplify. We see x plus 1 and x plus 1. We cancel those out, and so we get 1 over x squared plus 1. All right, so at this point we can figure out what is our vertical asymptote. Do we have any vertical asymptotes? We don't have any vertical asymptotes because in our simplified form, 1 over x squared plus 1, there's no x we can plug in to get 0. To show up in the bottom, right? X squared plus 1 has no solutions. It never intersects the x-axis if we think about it. So vertical asymptote, we have no vertical asymptote here. What about a horizontal asymptote? If we plug in for a horizontal asymptote, we see, look, the denominator has a higher degree than the numerator, so the numerator is going to eventually get crushed by that large denominator, so we have it eventually going to y equals 0. Let's look for some intercepts. Are there any intercepts? Can we plug in anything to get an intercept on the top? Well, in our simplified form, we're 1 over x squared plus 1. So there's no intercepts that we can get that will be x-axis intercepts, because there's nothing we can plug in to get a 0 to show up in our numerator. But we will be able to plug in 0 in for our x, so we can see what the y-axis intercept is. So we plug that in, and we get 1 over 0 plus 1, so we get just 0, 1. All right, so at this point, we can probably draw in our graph. So we don't have a vertical asymptote. We know that -1 is interesting, and we've got an intercept, so let's just make it even down the middle. Not quite sure how much will wind up showing up on either side, so let's just draw something to begin with. So 1, 2, 3, 1, 2, 3, 1, 2, 1. Great. So once again, every tick mark just means a distance of 1. We won't worry about writing in all those numbers. So at this point, they probably want a few more points, right? 0, 1. Well, let's see. Our horizontal asymptote is just our x-axis. Vertical asymptote, we have no vertical asymptote. We can plot in our intercept at 0, 1, so here is a point. And now let's start looking at some other points. If we plug in positive 1, 1 over 1 squared plus 1 gets us 1/2. Okay, 1/2. Here we are. We plug in positive 2, 1 over 2 squared, 4 plus 1, so 1 over 5, 1/5. Plug in 3. So 2, we're at 1/5. We're getting pretty low here. Plug in 3, 1 over 3 squared, 9 plus 1, so 1 over 10. We get 1/10. Now we're getting really low, so we get crushed down pretty quickly there. What about on the left side? Well, hey, look, it's x squared, and we don't have any other things there. So it's going to do the exact same thing on the other side, because -1 is going to square to effectively what it had been if it had been positive 1. -2 will go to positive 2, -3, positive 2. So -3 will also be 1/10. -2 will also be 1/10. And -1, wait a second, domain x is not allowed to be -1. So -1, this is actually a whole. So -1 is not going to be, it's going to be a location where you can see where it would have gone, but we're going to have to denote it with a whole because it's not actually allowed to show up there. It's allowed to be very close on either side, but at -1 precisely, it's technically forbidden. -1, we plug that in, we'd also get 1/2, but these are both going to be they're going to be a whole. So we can plot that point as if it was there, but we'll have to plot it with a whole because there it is not actually there. It's at that point, it disappears briefly. Momentarily, the function breaks and it just sort of isn't there. Now let's plug in the other -2. Oh, whoops, not 1/10. Sorry about that. Should have been 1/5. Wasn't paying attention. There, and then 1/10 here. Great. So at this point, we see that we're going to see some sort of curve like this, where over time it gets closer and closer, but then it flattens out, because we'll never quite touch that horizontal asymptote, but we'll get very, very close. This way as well, it gets there, it blips out of existence very, very briefly. For that single location of -1, it blips out of existence, and then it pops right back into existence. And then once again, it goes back to getting very, very close to that horizontal asymptote, but never quite touching it. So that's a rough, my drawing is not quite perfect, sorry, but that's a pretty good sense of what that would look like. All right, next one, f of x equals x squared minus 1 over x squared plus 1. Let's factor the top into its factors. We'd get x plus 1 times x minus 1, and it's divided by x squared plus 1. X squared plus 1. Great. So our domain, is there anything forbidden? Domain, nope, everything's allowed because x squared plus 1, we can never get any zeros to show up there, so all the real numbers are allowed in here. So there's nothing to cancel out. We don't have to worry about canceling out any factors because x plus 1, x minus 1, x squared plus 1 is irreducible, so it can't break in any linear factors to cancel with those linear factors up top. So at this point, let's see, are there any vertical asymptotes? So vertical asymptotes would be where the denominator is equal to 0. There are no vertical asymptotes because x squared plus 1, once again, there's nothing we can plug in to make it turn into a 0. What about horizontal asymptotes? There are there can only be one horizontal asymptote. My apologies. Horizontal asymptote, we compare the degrees. Squared here, both a quadratic on the top and a quadratic on the bottom, means that we're going to see a horizontal asymptote that isn't just the x-axis. So now we compare and we see what is the leading coefficients. We've got a 1 here and a 1 here, so we're going to see a horizontal asymptote of 1 over 1. And since 1 over 1 just simplifies to 1, we've got a horizontal asymptote of y equals 1. A height of 1 is what it will eventually slowly move towards. Let's look at what our intercepts are. So, can we get intercepts for our y-intercept? Yeah, we have no problem plugging in a 0. Nothing's forbidden, so we plug in 0. We get 1 times negative 1. Probably easier to actually figure it out from this equation up here. So negative 1 divided by positive 1, or just negative 1. We've got two intercepts at when the numerator becomes 0. So at negative 1, it becomes 0. At positive 1, it becomes 0. And we'll probably want a few more points, but let's draw this down so we can get a sense of what's going on first. So once again, we don't have any vertical asymptotes. We have nothing like special that we really want to look for. So let's just center our graph nicely. One, 2, 3, 4, 1, 2, 3, 4, 1, 2, 1, 2. Great. So we can plot in our intercepts. We've got intercepts. Well, let's first plot our horizontal asymptote, y equals 1. So we've got a dashed line at the height of y equals 1. Okay, no vertical asymptotes, don't have to worry about that. Intercepts, where are our intercepts? 0 is at negative 1. Negative 1 is at 0. Positive 1 also at 0. Probably want a few more points. Let's see what happens at positive 2, negative 2, things like that. So let's try those out. At positive 2, we plug that in, we get 2 squared minus 1, so that's going to be 4 minus 1, or 3 divided by 2 squared plus 1, that's going to be 5, so 3/5. Great. Let's try 3. Plug that in. We get 9 minus 1, 8 divided by 9 plus 1, 10. So 8 over 10. 8 over 10 simplifies to 4/5. And what about if we tried negative 2, negative 3? Well, notice we've got x squared up here. We've got x squared down here. So if we plug in a negative, it's going to behave just the same as if we'd plugged in a positive. So we see that negative 2 will also be at 3/5. Negative 3 will also be at 4/5. Great. Let's plot those points. Negative 2 is at 3/5, so 3/5 of the way up. Positive 3, I should have said positive 2 as well back there. Positive 3 is at 4/5. Negative 2 now is at 3/5. Negative 3 is at 4/5. We're going to see a curve like this, where it gets really, really close, but it'll never quite touch that horizontal asymptote. Goes through our points, nice, smooth curve. It's really close to the horizontal asymptote, but manages to never quite touch it, symmetric left and right. Great. Under our final example, this one's going to be a little bit of a doozy. All right, so x cubed plus 1 over x squared minus 4, and notice there's also this negative sign. Don't want to forget about that negative sign. So negative x cubed plus 1 divided by x squared minus 4. So first thing, we want to break this into factors because that's normally our first step. So how can we factor the top? Well, x cubed plus 1. How can we break that down? Well, we notice that we can definitely, if we plug in negative 1, that's going to turn to 0. So we know that x plus 1 has to be a factor. X plus 1. Now there's going to be some amount of x squared, some amount of x, some amount of constant. So constant, some x, some x squared. We've got x cubed, so it must be that there's only one x squared. We've got 1 at the end, so it must be a constant of 1 at the end as well, right? X times x squared is the only x cubes we'll get, so we want only 1 x cubed. 1 times 1 is the constant we'll get, so we want to make sure they're both 1. So now we need something in the middle that will cause the x squareds and the x to cancel out. So if we've got x squared here, then we need to have it be negative 1 here, so that when x times x here, it will come out as negative x squared because we've got positive 1 x squared. So those two cancel out. So we see that x cubed plus 1 is the same thing as x plus 1 times x squared minus x plus 1. So that's the same thing on our top. How can we factor our bottom for our thing? So for our rational function, that's going to break into x minus 2 times x plus 2. Remember, we had a negative sign out front in the beginning, so we've got a negative here still. So f of x equals negative x plus 1 times x squared minus x plus 1 over x minus 2 times x plus 2. Great, that's helpful. But there's something else we have to do. If we want to get to what the horizontal asymptote or slant asymptote is, let's figure out which one it is. Cubed here, squared here. So our numerator is 1 degree higher than our denominator, means we've got a slant asymptote. How do we figure out slant asymptote? Through polynomial division. So we want to do polynomial division on this. So x squared minus 4 divides into, now here's where things get a little bit tricky. We've got this negative here once again. So we can't divide into x cubed plus 1 because then we'd have to remember to deal with that negative. So we can make things a little bit easier on ourselves, and we can distribute that negative and we'll get negative x cubed minus 1, because that's the same thing as what was initially there, divided by x squared minus 4. So now we can be safe by doing that instead. X squared minus 4, so negative x cubed. How many x squareds do we have? 0 x squareds. How many x's? 0 x's minus 1. X squared minus 4, how many times does x squared go into negative x cubed? It's going to go in negative x times x squared, negative x cubed, negative x times negative 4 becomes positive 4x. We subtract this whole thing, distribute the subtraction. Negative x cubed plus x cubed becomes 0. 0x minus 4x becomes negative 4x. We bring things down. We got 0x squared minus 1. So we've got a remainder of negative 4x minus 1. And what came out was negative x. So what we've got is that f of x is also equal to, can be written in the form negative x plus its remainder of negative 4x minus 1 divided by x squared minus 4. Great, so now we've been able to figure out what the slant asymptote is. The slant asymptote is this negative x right here. Now, we might want to check this. It's easy to make a mistake with polynomial division it's just easy to make a mistake with polynomial division. So let's check it. Let's make sure that this f is the same as the f that we started with. So we can put this over common denominator, negative x times x squared minus 4 over x squared minus 4 plus negative 4x minus 1 over x squared minus 4. We distribute up here. We've got negative x cubed minus 4x. Let's combine our two since they are over a common denominator. X squared minus 4 plus negative 4x minus 1. So the negative 4x cancels with that was my mistake. Negative x times negative 4 becomes positive 4x. So it does cancel out. Positive 4x and minus 4x, they cancel out. And we get negative x cubed minus 1 over x squared minus 4, which, as we already talked about, is the same thing as negative x cubed plus 1. We can distribute that negative and we get negative x cubed minus 1. So checks out. That's good. Great. So let's see both of our two ways of looking at this. There's the factored form that we figured, and then there's also the polynomial division form. So the polynomial division form is necessary because it gives us our slant asymptote, and the factored form is necessary because it tells us our vertical asymptotes and also helps us figure out some other things. Hoi. And then also we just initially started with, just so we can still have it on our paper, so to speak, x cubed plus 1, negative x cubed plus 1 over x squared minus 4. That might be helpful since it's not that many numbers. It might be helpful for when we actually have to calculate some extra points. Okay, so what's allowed in our domain? Our domain forbids when x plus 2 or x minus 2 becomes 0. So that's going to happen at -2 and +2. So x is not allowed to be -2, it's not allowed to be +2. Where are our vertical asymptotes? Our vertical asymptotes, notice that there's no common factors between the top and the bottom, right? We've got x plus 1 and x squared minus x plus 1 on the top, and x plus 2 and x minus 2. None of these things have anything in common. They're not the same factor exactly, so we can't cancel anything out. So we've got vertical asymptotes at where we're forbidden for our domain, -2 and +2. What about horizontal asymptotes? We figured out it wasn't a horizontal asymptote. We figured out it is a slant asymptote because the degree was one higher in the top, so we'll write it as slant asymptote. But the idea in either case is the same thing. What happens in the long term to this function? That's going to be y equals -x, right? The part that in the long term, this part on the right that I just circled, it goes to 0, right? With very large x's, that thing will eventually get crushed down to 0. So we're left with just this thing in the box, the -x, and that's why it's our slant asymptote. And we might want to know the intercepts just because they're not too hard to grab. So we'll have intercepts. Intercept, we plug in 0. 0 plugs in -0 plus 1 over 0 minus 4. So -1 over -4 becomes +1/4. Let's plug in some other ones. -1 and 0. Sorry, we can figure that one out because if we plug in a -1 here, the whole top goes to 0. So that's our an x-axis intercept. So let's draw this thing in. It's going to be a beast to work with. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8. Okay, I'm going to mark in a location of 5, 3, 4, 5, just so we have a little bit of 1, 2, 3, 4, 5, a little reference that we can easily find our way around. 1, 2, 3, 4, 1, 2, 3, 4, 5, -5, 1, 2, 3, 4, 5, -5. Great. So we have a little bit of reference there on our thing. Now, let's draw in our vertical asymptotes. Vertical asymptotes at -2. And +2. And we have a slant asymptote at y equals -x. So what does that look like? Goes at a 45-degree angle, right? It's got a slope of -1. So for every step to the right it takes a step down. So it cuts through nice and, whoops, that was not quite as nice and even as it wants to be. Okay. So we see a slant asymptote like that cutting through the whole thing. All right. So we can plot our intercepts. 0 is at 1/4, so just above. And -1 is at 0. Now at this point we see, oh man, we need a lot more information, right? We need to plot a lot of points. So I've brought a bunch of points. I figured them out beforehand with a calculator. We don't have enough room to calculate it all by hand, and honestly it'd be kind of boring, but occasionally you will have to run through this yourself. So just be aware that when you need more points, you just work them through it, right? We've got -x³ plus 1 over x squared minus 4. We can just plot in points and figure them out. So let's look at what happens as we get close to this vertical asymptote of -2. So we plug in -1.5, and we find out that we are at -1.35. So we can plot that point, -1.5. We're at -1.35. Okay. And I'm just going to put down a whole bunch of points, and then we'll plot them all at once. 1, we're at 0.66, so 6 is repeating. So if 6s are repeating, it's just 2/3. What about -3? We're at 5.2. At -4, we're also at 5.2. That's interesting. -5, we're at 5.9. At +3, we're at -5.6. At +4, we are at -5.42. At +5, we are at -6. Okay, that should be about enough for us to figure things out. So at +1, positive 1, we're at 0.66666, or we are at 2/3 more accurately. We also might want to know where we are at 1.5. Didn't do that one. Whoops. But 1.5, we could figure that out. 1.5 cubed plus 1, 3/2 cubed. That's a little difficult. It's going to be, we know it is going to wind up going up here though, because if we think about a number that is just a little under 2, then just a little bit under 2 is going to cause this bottom part to be negative, and it's going to cause the top part to remain positive, so negative in front. Remember, can't forget about this negative in front. So negative in front, positive on top, negative on the bottom, cancels out when we get positive, so we're going up this way on this side. And when we are at negative 1.999 just to the right of our vertical asymptote on the left, we know that we're going to be going down because we see at negative 1.5 we're going down already. If we consider negative 1.99999, x squared minus 4, that's once again going to be negative because it's smaller. X cubed plus 1, negative 1.99999, that's going to make a number that is negative on the top because it'll be negative. Negative cubed is larger than the positive 1. Negative 1 point anything cubed is going to be larger than positive 1, so that'll be a negative. So we've got a negative on the top, negative on the bottom, negative in front, comes out to 1 negative left, so we're down here. What about a little bit to the left? If we were at 2.0001, then the x squared minus 4 will wind up being a positive because it will be just large enough to beat out that negative 4. X cubed plus 1, still going to be negative, but we've got that negative in front, so it cancels, so we'll be going up on this side. And over here at positive 2, a little bit over 2, x squared minus 4, if we're at 2.0001, that squared minus 4 is going to be larger than the minus 4, so it will be positive. X cubed plus 1 remain positive, but we've got that negative in front, so it'll be going down here. So now we know the directions of all our asymptotes. Let's plot in the rest of our points, and we'll be ready to draw this sucker in. 1, 2, 3, 5.2, so 5, and just a hair up. Negative 4 is going to be at 5.2. Negative 4 is going to also be at 5.2. My graph is a little bit high on the y equals x. My graph is not quite perfect, sorry. Negative 5 will be at 5.9. And if we go this way, we're going to go up here. So one thing to notice is that we're actually going, we wind up being, there's something odd going on between negative 3 and negative 4. If we were to calculate another point, we might want to try like negative 3.5 or negative 3.2 to get a sense of where it's lower. We would eventually notice that it actually dips down, hits at absolute lowest minimum around here. We could figure that out precisely if we had a calculator and a lot of time. 3, we plug in 3, we're at negative 5.6, so a little below. Here we are. At 4, we're at negative 5.42. Once again, there's that interesting thing where it will curve back up. Turns out that the minimum is somewhere between those two. At positive 5, we're at negative 6. Once again, my graph of the green slant asymptote isn't quite perfect. Probably really my red axes aren't quite exactly the same scale. The problem with drawing it all by hand without having a ruler. But at this point, we're finally ready to graph this thing. So we're going to get on this side of the slant asymptote, this side of the slant asymptote. So in the middle part where we don't have to worry about the slant asymptote because it's too close to these verticals, we're going to be like this. When we have the slant asymptotes, we'll be pulled off this way, and then we get pulled along the slant asymptote here. And we'll get closer and closer over time. Pulled along the vertical asymptote, then it goes dips, and then it gets pulled along the slant asymptote. Wouldn't curve away there, that's just my imperfections. There we go. And then it gets closer and closer to that slant asymptote the whole time. It's pretty tough to draw something this complex, but this is absolutely as complex as you're going to wind up seeing in a class or have any homework or tests have to do. So at the worst case, you just wind up having to take a lot of points, plot a bunch of points, and you can figure out how this thing behaves. You can figure out where the asymptotes are, you can figure out the slant asymptote, horizontal asymptote, vertical asymptote, all that business, your domain. You can figure out all these things, and when it comes time to graph, you just have to punch out a lot of numbers so that you can actually see what the picture looks like. But all in all, it's not that hard if you just make enough numbers. All right, hope everything there made sense, and we'll see you at educator.com later. Bye.